So let's start with experiment number 1. So which is the aim of the experiment is to find the resistance per unit length of a given wire by plotting potential difference versus current graph. So this is the wire that will be given. So you have to find the resistance of this wire per unit length. So the principle involved is obviously Ohm's law. You have to write the principle, which is the current flowing through the conductor, through the ends of the conductor, is directly proportional to the potential difference applied across the ends of the conductor, given that the surrounding conditions such as temperature is a constant. So just write V is equal to IR, where R is the resistance with the SI unit ohms. Now the formula and the nature of the graph. So this is the nature of the graph. Basically we can see that V is equal to IR is a linear graph. So that means if V increases, I also increases. So it's directly proportional, it is linear. So therefore if we plot a graph between V and I, it should be a straight line. Now if we calculate the slope, so basically choose any 2 points, make a triangle, and then slope is given by tan theta, which is opposite by adjacent. So you can see if this is theta, opposite is this value, which is equal to delta V, and adjacent is delta I, because the x-axis is I, so it's delta I. So from Ohm's law we know that delta V by delta I is R. So you can see here V by I is R, so delta V by delta I is R. So slope will basically give me resistance, and then I have to calculate resistance per unit length. Now, so the observations that we have to calculate is obviously the length of the wire. So we can calculate the length prior to starting the experiment, and then we have to calculate the least count of the voltmeter and ammeter involved, and this is the observation table. At least 5 observations should be made since we are plotting the graph. So first let us find out the least count of voltmeter and ammeter. So this is an ammeter. So let's see, it's in milliammeter. So to calculate the least count, just choose any number. Let's say for example I am choosing 50 milliampere. Then I have to count how many divisions are there between 0 and 50. There are 10 divisions. You can see 1, 2, 3, 4, 5 and so on. Up 10 divisions are there between 0 and 50. So the least count of this ammeter is 50 milliamps by 10, which is 5 milliamps. So I can write here the least count of ammeter is 50 milliamps by 10. So that gives me 5 milliamps. Similarly, voltmeter, I'll choose this number, that is 100 millivolts, and there are 10 divisions between 0 and 100. So my least count of voltmeter is 100 millivolts divided by 10, that is 10 millivolts. So it's 10 millivolts. So if you wish, we can change it to volts also. That means milli is nothing but 10 to the power of minus 3. So the least count of voltmeter would be 10 into 10 power minus 3 volts, and least count of ammeter would be 5 into 10 power minus 3 amps. So this is the circuit diagram. So first draw that circuit diagram with polarities. So this is the battery positive, which is connected to milliampere or ammeter, whatever it's given. So positive of that, and the negative. Remember that for series connection polarity will change, and for parallel connection polarity won't change. So as you can see, millivolt or voltmeter and resistance, unknown resistance, are in parallel. So you can first make that connection first. So basically, like what I have done here, this is the given wire of which resistance I have to find. So I have connected its ends across the voltmeter. So that's a parallel connection. So as you can see, this is the 2 ends of the resistance which I have connected across the voltmeter. So that's parallel connection. So basically this connection is over. So resistance to voltmeter, this connection is over. Now I have to make the other connections, that is from battery positive to ammeter positive. So this is the connection, battery positive to ammeter positive. Then ammeter negative is going to voltmeter positive. So ammeter negative is going to voltmeter positive, and then voltmeter negative is going to rheostat. So voltmeter negative is going to rheostat. So please ensure that you are connecting one end of the rheostat here, that is on the upside, because if you connect it here across these 2 ends, the rheostat will behave like a standard resistor. So one of the connections should be on the upside here. and one more connection from here back to the battery. So this is the setup for resistance per unit length. Now let us start taking readings. So I have put the voltmeter at 4 volts. You can put 2 volts or 6 volts or whatever. Now then I have to move the rheostat, and that will change the current. So at this position of the rheostat, that means here, I am getting this reading. As you can see in the milliammeter, the red needle is 15 divisions away from ahead of 0. So we know that least count of ammeter is 5 milliamps. That means one division is 5 milliamps. So 15 divisions must be 15 into 5, which is 75 milliamps. Similarly, in voltmeter, we can see that the red needle is 3 divisions away from 0. So one division is 10 millivolts. We have seen that. That's the least count. So the voltmeter reading is now 3 into 10. That is 30 millivolts. That's what I have written here. Now for the next readings, you have to move the rheostat in either of the directions, and that will change the current and the volt potential difference, or volt potential also. So you have to take at least 5 readings. Let us see one more reading. So I have moved the rheostat further away. Now the ammeter reading. So the red needle is about 10, 20, 25 divisions ahead of 0. So 25 into least count of ammeter, which is 25 into 5. So that gives me 125 milliamps. That's the ammeter reading. And the voltmeter reading, you can see it is 5 divisions ahead of 0. So 5 into 10, because 10 is the least count of 10 millivolts is the least count of voltmeter. So it's 5 into 10, so that's 50. So 2 more readings to go. So these are the readings that I have obtained. So I already know that this is voltmeter reading, that is V, and this is I. So I have just calculated R just for my own reference. So R is equal to V by I. So 30 into 10 power minus 3 divided by 75 into 10 power minus 3. 10 power minus 3 minus 10 power minus 3 cancels out. So I am getting these readings. You can see that it is almost consistent, that is 0.4 ohms, except these two readings, it is 0.35 and 0.32. So this much of deviation is fine. So this looks okay. So now we have to plot the graph between V and I. So as you can see, this is the graph that came out. You can see that it's not a perfectly straight line. It looks like that because the scale is very magnified. So even though a little deviation looks magnified here, so you could take a better scale to hide the deviations from the straight line. That is also possible. So here the scale I have taken is, okay, x-axis first of all is current and y-axis is volt potential difference. I have taken 1 centimeter is equal to 25 milliamps, and here also 1 centimeter equal, here 1 centimeter equal to 5 millivolts. So that's what I have taken. If you wish, you could take something else also here. You could take 1 centimeter is equal to 10 milliamps. That's also possible. So I have started from 50 here, 50 milliamps. I can start from anywhere. You can see that my current value starts from 75 and it ends at 250. So that's why I have started from 50. I could have started from 75 directly also. And my voltmeter reading starts from 30 and ends at 80. So that's why I have started from 25. Could have started from 30 also. And I have ended at 80. So here 1 centimeter is 5 millivolts and here 1 centimeter is 25 milliamps. Now when I plotted, so these are the points I got. So the straight line should be such that it should be weighted average. So that means I have, see, for example, this point is outside the straight line and it's below the straight line. To compensate for that, this point is above the straight line. So that's how we should draw. So this is the best possible fit, at least by hand. So then you have to choose any 2 points and make a triangle, and then you have to calculate the slope. So slope is nothing but tan theta, which is opposite but divided by adjacent. So here this value you can see here, it is about 70, and the very next division is 70.5. Why is it 70.5? Because we already know that there are 10 divisions. The 10 divisions are equivalent to 5 millivolts. We already see that 1 centimeter is 5 millivolts. So 5 by 10 is each line is equal to 5 by 10, 5 millivolts by 10. So that means it's 0.5. So if this is 70, the very next division is 70.5, and 71, 71.5, and so on. So this point was 72. So that's why I have written 72, and this point is exactly 55. So this length I have got is 72 minus 55. Similarly, this point is equal to 200, whereas this point corresponds to 150. So it's basically 200 minus 150, which is 50. So 72 minus 55 is 17 millivolts divided by 50 milliamps. Milli cancels. I am getting 0.34 ohms as the answer. So this is the resistance of the wire. If I calculate the average of the resistances I have got here, the average I'll get is 0.37. So from the graph I got 0.34. There will be some differences, but okay, approximately it's fine. Now what you have to do, you got the resistance as 0.34 ohms. Now you have to measure the length of the wire using the meter scale, and the aim of the experiment says you have to find the resistance per unit length. So you have to basically find 0.34 resistance divided by whatever the length, say it is 50 centimeter. So you have to calculate this value and write with SI unit, which is ohm per centimeter. You could wish to convert it to meter, but if you leave it like this, that's also fine. So that is the result of the experiment. I have written the result also. So this carries 2 marks if you write the result along with the units. So the result of the experiment is the resistance per unit length of the wire is 0.0068 ohms per centimeter. I had got the resistance as 0.34 divided by 50 is I get 0.0068.